Good morning to all of you. Myself, Dr. R.K. Jain. In this session, we will learn about application of B-Spline's method for solving partial differential equations. I am team leader of this program, RC1350. So first we discuss about introduction to splines. In theory of spline functions, a total different approach which is called collocation method by using piecewise polynomial have been developed to find approximate solutions to both ordinary and partial differential equations. Such methods are very elegant and their simplicity and economical in different field of applications. They are applied directly to the original differential equation that describes the physics of the problem. The B-spline collocation is one of the spline collocation method. The choice of collocation method is influenced by continuity and degree of splines. B-spline method is more efficient than those methods which require integration of the differential equation. The success of the B-spline collocation method is dependent on the choice of B-spline basis. The B-spline functions constitute a complete set of basis functions that will approximate a given function in the referred range of interest. B-spline curves are also has superior properties that make them suitable for shape presentation. Now question arises, why we need splines? Piecewise polynomial approximations allow us to construct highly accurate polynomials, but it does not always produce approximations that are pleasing to eye. This occurs because the approximate function is not smooth at the junctions between separate pieces of the piecewise polynomials. While we have polynomials, QD is continuous, it is not continuously differentiable on the entire interval of approximation. The graph of the interpolant can have kinks in it. By using splines, we try to address this problem. Now, definition of the problem. Suppose we are given a set of nodes xi at which we wish to interpolate a function fx with a spline of degree d. The problem is then to find a piecewise polynomial function qd that satisfies the following condition. Number 1, interpolation, 2, smoothness, and 3, interval of definition. Now B-spline is a spline function that has minimal support with respect to given degree, smoothness, and domain and partition. The term B-splines was coined by Isaac Jacob Schonberg in 1966 and it is short for basis spline. B-spline can be evaluated in a numerical stable way by DeBoer in 1972 by giving a algorithm. Now definition of B-spline, the ith B-spline basis function of d degree denoted by BID and is defined as BI0 equal to 1 for the interval xi to xi plus 1, otherwise 0, and BID is given by the following recurrence relation. Some facts about B-spline. BI0 is a step function equal to 0 everywhere except on the half open interval where x belongs to interval xi plus 1. Now Computation of set of basis function require a specification of a node vector x and degree d. The half upper interval is called the ith node span. The computation of the d degree function generates a truncated triangular table. Now collocation points. In the B-Spline collocation approach for solving differential equation, specific quantities that define the spline curve or surface must be required. For collocation, the location of the nodes or nodes and the value of the Debord points must be determined. These nodes or nodes are called collocation points. The node location should be chosen in such way so that they provide sufficient resolution for the solution. The values of the Debord points are found by forcing the differential equation to be satisfied to some tolerance at the finite set of evaluation or collocation points. Now important properties of B-Spline. Number 1, B-Splines having compact support property, non-negative property, partition of unity, all derivative exist in the interior of a node span. Now definition of B-Spline. When the B-Spline is uniform, the basis B-Spline for a given degree n are copies of each other. Now derivation of cubic B-Spline formula is given in this way. Now derivation of quantic B-Spline is given by this formula, and it is defined in this way. Now here it is graph of cubic B-Spline. Now this is graph of uniform cubic B-Spline. Now we use cubic B-Spline for solving nonlinear partial differential equation. For this purpose, here we consider RLW equation, which is given in this way: ut plus ux plus uxx minus mu xxt equal to 0. Here we are having boundary conditions. The exact solution of equation 1 is given here in equation 3. Now step 1, first we divide the interval AB into n equal parts, x0, x1 up to xn. Let Bi be the cubic B-Spline at the node points xi. The set of splines form a basis function defined over the interval AB. Now a global approximate solution unxt is expression in terms of the B-Spline or unknown time dependent parameter is unxt is summation from I equal to -1 to n plus 1 cit bix, where cj are unknown time dependent quantities to be determined from boundary conditions and collocation conditions. The values of bix and its derivatives, first derivative, second derivative at the nodes are given in the following table 1. So by using these definitions, we approximate this ui equal to ci minus 1 plus 4ci plus ci plus 1. First derivative in this way, second derivative in this way. Now let us write equation 1 in this form, and if the time derivative is discretized in a simple finite difference fashion, del u over del t equal to ui plus 1 un plus 1 minus un upon k, where k equal to tn plus 1 minus tn. Then equation 6 takes form, which is given in the equation 7. Now linearizing the nonlinear term at the points using the following formula, which is given in equation 8. Then using 8 in equation 7, it takes form equation 9, where we have this equation where AI is given by this, BI is given by this, DI is given by this, and FI is given by this. Then the system 11 can be written in the symbol form in this way. Then this set of equation is the recurrence relationship of element parameter vector dn, so that n plus 1 equation by n plus 3 unknowns at each time label n. Now using boundary conditions in the same fashion, then we get the system of matrix form at time label n becomes in this way. The above system requires two initial level values at t equal to 0 and t equal to k. So we use the exact solution to determine these initial conditions. Now we get, first we find initial vector in step 7. So the equation lead the system n plus 3 by n plus 3, which we convert to a tridiagonal system of order n plus 1 into n plus 1, and we solve this by using Thomas algorithm. In the same way, we use quantic B-Spline collocation method for solving fourth order parabolic partial differential equation with redefined basis functions. Description of method is similar as we have already discussed for cubic B-splines. Quantic B-spline defined in this way. Here we find different derivative, first, second, third and fourth for quantic B-splines. Now we approximate equation 6 by using quantic B-splines. We get equation 7. In collocation method, the basis function should vanish on the boundary where Dirichlet type of boundary conditions are specified. We use this concept. We redefine the basis function in equation 12. Then we use this technique for solving fourth order parabolic equation. We discretize this equation by using quantic B-splines, and here we have shown the results where first column indicate value of x, second solution by the proposed method, third exact solution, and last column shows absolute error. So here we have seen the absolute error is e to the power minus 0.5, which is similar to exact solution. Thank you.